Here we are, it's part 10, page 917 of the nutrition chapter in metabolism. And here we are now looking at the inside of the cell. You have to imagine here that we're inside of a cell on this page. And here in the cytoplasm we have glycolysis going on. And we have glucose that's basically being metabolized to pyruvate. From this set of reactions right here, we get 2 ATPs. Okay, total. From one molecule of glucose literally to 2 pyruvic acids, we end up with 2 ATPs. Now we're going to enter the Krebs cycle, and that means that we're going to be having more substrate. That is to say, just from the interaction, the oxidation of individual molecules one to the next, we get some energy out of the deal. So we get 2 more ATPs right there. That's what you need to know. Okay, and then we get this coupling that occurs with NAD and FAD. Okay, and so this is called coupling, or they're transferring the hydrogen ions over here, and we're getting the electron transport chain, and ultimately we're actually creating ATP here. Through the, we'll talk about how that mechanism works. There's a special channel that synthesizes ATP. And we get 34 more ATPs right here, so that's a total of 38. So 2 from that substrate workout right here with glycolysis, 2 from Krebs cycle, 34 from oxidative phosphorylation, 38 total. Notice that we're going from the cytoplasm into the mitochondrion here. This whole organelle here is a mitochondrion. We have the Krebs cycle inside the mitochondrion. It's the only place where it is. We have the oxidative phosphorylation also inside the mitochondrion. It's the only place that it is. Okay, then. Here we're looking at the glycolytic pathway. The caption here on page 918 is the 3 major phases of glycolysis, or the glycolytic pathway. Phase number 1, we go from glucose, a 6-carbon molecule. They show the little 6 carbons there. We get to this next stage here. We're producing some ATP. We phosphorylated the molecule, changed it a little bit, and then we're going to break this down, and we're going to follow 2 different pathways and come back together again. We have a glyceraldehyde, and we have a dihydroxyacetone phosphate. It's phosphorylated. Then we come down, we produce 4 ATPs over here, and this brings us to pyruvate. We're actually using energy to make energy in this situation, so we're actually only getting 2 net out of here. I don't know why they're not showing us that. Why are you not showing us that? But anyways, we're not going to worry about it. At any rate, you'll just have to trust me on that. So on 2 pyruvic acids, 2 3-carbon molecules right here, we're going to, at this point, we're going to just stop. Because what if we're sprinting right here? What if we're lifting weights right here, going for the burn, right? So in this case, if we don't have any oxygen here, they've crossed out the oxygen, then ultimately what we're going to end up with is lactic acid, which I have a little equal sign here. That's the burn. Okay. Then if we start to breathe properly and slowly, and we are able to press on forward, the pyruvate goes to acetyl-CoA, enters the Krebs cycle, and now we're all set. And this requires oxygen. So this is the oxidative phosphorylation stage. Okay, and then we press on from there. And we take a look at the Krebs cycle. Here is the Krebs cycle, and we've gone from pyruvate, and we've come to acetyl-CoA. So that's an important step in all of this. One of the things that they're not showing you in this is that we actually use some of the CO2 to come over here, and we're going to make this molecule of interest. Whoops, not that one, but this one. Actually, they are kind of showing us what's going on here. We're making oxaloacetate. So we need to add acetyl-CoA to oxaloacetate. And the key function here is that we need glucose to do this part of it. If we're burning fat, it turns out fat is going to burn in a flame of glucose. So any distance runner understands that. A marathoner knows, don't go through your glycogen too fast, right? So you've been packing on the glycogen, so to speak, by having a nice carbohydrate-rich meal the day before of your race, and now you've got plenty of sugar to burn while you are burning your fat. Most of the time, 60 to 70% of the energy of a well-balanced and homeostatically fit muscle system is going to use 60 to 70% is going to use fatty acids, and the rest of it's going to be powered by glucose. Glucose, in order to make acetyl-CoA, I'm sorry, not acetyl-CoA, but in order to make oxaloacetate, you have to burn some sugar, then you can bring in the fatty acids, beta oxidation. We'll get to that in a second. And here are the molecules of interest here. Each one is becoming a step down, more how shall I say, the oxidation number is proceeding through here. We're oxidizing one molecule to the next, and we're getting energy. Here we have the energy to add hydrogen to an NAD. We have some more energy. Carbon dioxide is coming off here. Okay, and so we continue on down through here. Here, this is a highly energetic reaction from succinyl-CoA to succinate, and we get ATP. And over here, we're going to add hydrogen to the riboflavin, so we get FADH2, right? That's a 2 flavonoids. And so we get another, over here, we get another niacinamide with a hydrogen added onto it. Okay, so these are important details. We're going to actually spin the Krebs cycle twice. So we're going to get 2 ATPs from this, and we're going to get lots of reducing equivalents, which is what those are. We come over here with our reducing equivalents, and we toss our hydrogen into the mix here. The electron comes off the hydrogen and goes through the electron transport chain here, and the hydrogen ion proceeds through these channels. Do you see how we're pushing that through? This is an energetic pathway, and then once the hydrogen goes through, it comes in this way. Normally, what this is that this is a mechanism for a bacterium to pump hydrogen out. That's what bacteriums do. They ferment sugar and they pump hydrogen out. That's why your teeth are being etched, is because of that fermentation and the hydrogen, the acid that etches the teeth. Right, so we're making this work backwards now. It's the same molecule, it's ATPase. Normally it pumps things, but now instead we're using the ion that would normally be pumped. We're pushing the ion through, and we're making this part of the mechanism go backwards. Instead of breaking down ATP to pump hydrogen, now we're pumping hydrogen and we're making ATP. So that's the key factor right there. That's a very important understanding to have. Here they're showing us the electron transport chain. Unless you're a physicist or a physical chemist, maybe you're not interested. Ultimately, though, oxygen is going to be the final electron acceptor. So oxygen picks up the electron, oxygen picks up the hydrogen, and we end up with the waters of metabolism. A very poetic scenario. Okay, so if you were a bacterium, you'd be going this way. You'd be actually pumping hydrogen, but you're not. You're a human, so you're working it this way. You have it in reverse order, and you're actually pumping this way, or forcing the hydrogen through, which forces the pump to go and make ATP. So that's the key factor here.